Okay, in this video we are going to continue doing some KC calculations, but we are going to look at some things that you can do for some questions that are going to kind of make it a little bit easier. So in some cases, you are going to get a really small KC. When you are given a KC that is very small, you have to kind of remember what that's telling you, right? If you think about it, we talked about K being equal to 1, greater than 1, or less than 1. We said that when K was less than 1, that meant reactants were favored. So what happens in some cases if K is small enough, we actually find that the amount of reactants that produces products is very minimal. So when we think about our ice charts, right, the fact that we would have that initial concentration, let's say is 0.1, our change would be minus x, and our equilibrium would be 0.1 minus x. We find when K is really small, we get a really small x. So if I were to do like 0.1 and then I would subtract, I don't know, 4.5 times 10 to the negative 5. If I then round for significant digits, I still have 0.1. At which point it didn't really change. So what this means is we can do something to make these questions a little bit simpler. And why it makes it a little bit simpler is we're going to do what we call the approximation method. So in the approximation method, what we say is that because K is so small, the initial concentration of the reactant is going to be the same as the equilibrium concentration of the reactant. Okay, this isn't true for the product because we will make some. It's just going to be a really tiny number. Okay, so how we are going to decide if we can approximate. The general rule is to take your initial concentration and divide it by K. And then either we're looking to see if we get a number greater than 1,000 or a number less than 1,000. And this basically indicates to us how small that X is going to be with respect to that initial concentration. So if you're given more than one initial, general rule is use the smaller one. So we're going to take whatever the initial is, we're going to divide it by that numerical value of Kc. If we get a number less than 1,000, that means K isn't small enough to approximate. You're going to do this question like you did all the ones in previous questions. If, however, you get a number greater than 1,000, so you get this option here, that means you can approximate. Okay, that means K is small enough that once we actually figure out X and we do that initial minus X and then we round for significant digits, we still have that initial amount. So this is going to make it easier because it's going to get rid of some X's for you, and it's going to generally make it a much simpler question to solve. So let's look at an example of how you're actually going to do this. So consider the following equilibrium reactions. We have N2 plus O2 give us 2 NO2. We're given the value of Kc. It's 4.2 times 10 to the negative 8. Right? That is a small Kc. It's times 10 to the negative 8. So definitely want to check for approximation. You may honestly even find that you want to do an approx check on every single question because sometimes you guys just forget to do it and then you get a question where you could approximate and you don't, and then you don't solve it right. Not that you'll get it wrong if you don't approximate it. If you do it right, you'll still get the right answer, but the issue tends to be these are more challenging questions if you don't approximate them. So the odds of getting it incorrect can be a little bit higher. Okay, so we are still going to start by setting up our ice table. Okay, so we have our nitrogen. Where's this typing? Apparently it's typing nowhere. And it's typing really weird for some reason. Let's try this again. Okay, we have our nitrogen. There we go. And then what else do we have? We have plus oxygen. And that is going to give us 2 nitrogen monoxides. Okay, so going to set up our ice chart the same way we always do. That's never really going to change with any question. The only time you're not going to set up an ice chart is if you're given all equilibrium values. And then you don't need to set up an ice chart because obviously you're plugging right into it. So we have initial, change, and equilibrium. Okay, just move these a little closer so it's not going to take up quite so much room on the slide. All right, so what do we have in the question? So we were given the value of K we were given a constant or moles, sorry, of nitrogen, so 0.085, and we were given moles of oxygen, 0.038, in a 1 liter container. So because it's a 1 liter container, the moles is going to be the same as the concentration. So for nitrogen, 0.085, for oxygen, 0.038, and then for oxygen, just 0 because we weren't given any initials for it. Okay, change values, minus x, plus 2x, right? And plus 2 because this balanced with a 2. So equilibrium-wise, 0.085 minus x, 0.038 minus x, and 2x. So now this is where we're going to add in that additional little piece. We are going to go and we're going to go do that approx check. So how we're going to do that approx check, we said we were going to take the initial concentration. In this case, I have 2 of them, so I'm going to choose the smaller one, so 0.038. And we are going to divide it by our Kc, which in this case is 4.2 times 10 to the negative 8. So we're looking to see if we get a number greater than 1,000 or less than 1,000. So 0.038 divided by 4.2 times 10 to the negative 8, I'm getting 904,000. So that's way bigger than 1,000. I can approximate. So I'm just going to put a little check mark next to the approx, which means that I can. So what does this mean I'm going to do differently? So because I can approximate, that means for my reactants and my reactants only, I can get rid of this x. Okay, and that's because this difference of 1,000 is telling us that whatever the numerical value of x is, it's going to be really, really tiny. So when I actually go back and do this 0.085 minus x and then round for significant digits, I'm still going to have 0.085. So if I'm still going to have the same number, we may as well just leave those x's out, and it makes this calculation much simpler. Like I said before, if you don't recognize and you leave them in, it's not really going to change anything besides make the question harder. You should still get the exact same answer in the end. You might find that the very last digit is off by 1, but it doesn't really matter. Okay, so now that we've decided we can do that, we're going to go ahead and we are going to set up our Kc expression just like we always do. So we are going to have the concentration of NO squared, and that is going to be over the concentration of N2 times O2. Okay, so we know what our Kc is. It's 4.2 times 10 to the negative 8. Okay, and this is going to equal that 2x squared. Well, that's not a square, that's a square. Okay, do be careful when you plug this in with that square, because sometimes some of you will put this in and you won't put the brackets, and you're going to write it as 2x squared. And that's not the same as this, because this is really 4x squared. Whereas if I wrote it this way and I didn't put those brackets around, I might not notice that that square also applies to the 2. So do be really careful when you write stuff out to either use the brackets, or when you write it out as 4x squared so you don't later on get confused with what you have done. Okay, so we have our 2x squared, and that is going to be divided by that 0.085 times 0.038. Right, so you should be able to see how already this question looks much simpler than it would have looked like if we had left that minus x and minus x in. Right now we only have the 1x, we have a whole bunch of numbers. It's a much nicer question to solve, right? So our next step is going to be to do that 4.2 times 10 to the negative 8 and multiply it by that 0.085 and that 0.038. So 4.2 times 10 to the negative 8 times 0.085 times 0.038. So when we do that, we get 1.3566 times 10 to the negative 10. And that's going to equal that 2x squared or 4x squared, however you want to write it. Okay, so To solve for x, our next step is going to be to take square root of both sides, right? Because we need to get rid of the square, right? That'll get rid of that. And then once we take the square root of that, we then need to divide by 2, right? So that we can get rid of that. And then we are left with x. So square root of our answer, we get our number, we divide by 2, we get a very small x, which is what we were expecting, right? If I get an x that isn't very small, then either I've done something horribly wrong or I made a mistake and I couldn't actually approximate, okay? But either way, you've done something wrong. So 1.8, or not 1.8, when I say 5.8 times 10 to the negative 6 is what I'm getting. Okay, there's more numbers than that on my calculator. I'm just only writing those two because this has 2 significant digits and that has 2 significant digits. When I go ahead and do that 2x, I'm obviously going to use the number that's on my calculator, so I guess I could write this as ... just to make it obvious that I'm not rounding, right? Because I don't want to round until we get to the end. So the question was asking me for the concentration of NO at equilibrium. I know that it's equal to 2x. I've now figured out what x is equal to. So I'm going to take my answer and I'm going to multiply it by 2. And I now get that the concentration is going to be 1.2 times 10 to the negative 5. Make sure you don't forget to throw in that unit of concentration, okay? So check to see if you can approximate. When you see that the k is small, right? So as soon as you see the k is something times 10 to the negative, usually a good check to do a quick approx check. Again, though, if you want to do an approx check with every question, you definitely can. If you miss that you could have done an approx, it doesn't make it unsolvable. You can still get the exact same answer. You're just going to do more work to be able to get to that final answer, okay? All right. I think for the safety of time, I'm actually going to skip the next 2 slides because they basically look exactly the same. With this one here, you can see k is times 10 to the negative 18. You're going to be doing that approx check. I'm going to do the same thing. You will notice, though, that on D2L, the full answers to these questions will all be posted. And so if you need to get those, you can get those from there. Okay, so now we're going to look at a slightly different situation. So far in every single question that we've done, you've only ever been given initial concentration of reactants. You have never been given initial concentration of products. We've always assumed that they were 0 because we weren't given anything. Because they were 0, we were always able to assign our change values as negative x's on the reactant side and positive x's on the product side because we knew it had to shift that way. But if you're given initial concentrations for everything, you don't actually initially know which way it is going to shift, okay? So in questions like this, there's 2 ways that you can approach it, okay? One way is to look at the numerical value of k, because remember the numerical value of k gives you an indication of what is being favored, right? K is greater than 1, we know products are favored. So around 1, we know that they should all be about the same. If it's less than 1, then we know that reactants are being favored. Why that's helpful, I can look at what my initial concentrations actually are. And do they line up with that or not, right? If they don't line up with that, then I know which way it has to shift, right? If my K tells me reactants are favored, but I have way more products than reactants, I know it has to shift towards the reactants. So that's one way you can do it. Some of you guys like that way, some of you prefer a math way. So the way that you can look at it mathematically is using what we call a reaction quotient. So symbol for the reaction quotient is this Q right here. So we calculate a reaction quotient the exact same way we calculate a K. The only difference is we don't put in equilibrium concentrations. We throw in those initial concentrations. And then we get a number, and then we can figure out from that number which way it needs to shift. So if we throw those initials in, and we get a Q that's equal to the K that we've been given, then what we actually have just figured out is that it's already at equilibrium because those concentrations represent those equilibrium concentrations. If we find that the Q is greater then if you think about how we calculate it by doing products over reactants. So if Q is greater than K, that's telling me right now I have too many products and it has to shift towards reactants. Okay, so that would then mean my products would get minus X and my reactants would get plus X. If I find the opposite and I find that Q is less than K, that means I have too many reactants on the bottom and I need to create more products. So it's going to shift the way our reactions generally shift, and it's going to go ahead and shift to the right. And our reactants will get the negative X and our products will get the positive X. So the only nice thing with questions like this is if you mess it up and you don't shift it the right way, you don't have to completely redo the question. What you'll find is you're going to get to the end of the question, you're going to have a negative X. So you can't have a negative X. It's not a doable thing. You have to have a positive X. But what you can do is instead of erasing everything, just switch your positive and negatives around in your ICE table and the sign of your answer, and it's still the exact same numerical value. Obviously, you can still definitely go ahead and plug your answers back into K to make sure that it works, right? That's kind of the best way to check that you have done the question correctly. So let's have a look at one like that. So it says, consider the following reaction, N2O4 to give us 2NO2. The Kc for this reaction is 0.023. So if the initial concentration of dinitrogen tetraoxide is 1 and nitrogen dioxide is 3, what will be the equilibrium concentration of both species? So we start with our ICE table because we pretty much always start with the ICE table. So we're going N2O4 gas to give us 2NO2 gas. Okay, so initial concentration, we are given the initial for the N2O4 as being 1, and the initial for the NO is 3. So, change value. Keeps defaulting to red, and I'd like it to do blue. Okay, here we go. All right, so change value. I know that this is going to be an X, and I know this is going to be a 2X, right? Based off of the coefficients we balanced with. But what I don't know right now, because I've started with initial concentrations of everything, is this shifting this way to the right, which would make this a negative and this a positive, or is it shifting this way to the left, which would make this negative and this positive? So 2 ways I can do this. One way I can do this is I can look at Kc. So Kc is 0.023, so it's less than 1. So a Kc being less than 1 tells me that reactants should be favored. Right now, if I look at these concentrations, I have more product than I do reactant. So I can decide from that that this has to shift this way to make more reactants and have less products so that I actually represent what I have here. Okay, so that means this is going to be a plus X, this is going to be a minus X. Okay, if you're like, I don't like that, that doesn't really work for me, the other thing I can go ahead and do is I can calculate that Q value, okay? So to calculate that Q value, we're going to calculate it the same way we would a K. So we're going to do the NO squared divided by the N2O4. So we're going to do 3 squared, that's not a square, and then we are going to divide by 1. So if we do that, we get 9. Okay, when I look at that Q, it's 9, it's supposed to be 0.023. We said that when Q is greater than K, we need to shift to the left, right? So 2 potential ways, they both tell me the exact same piece, which is that I need to shift to the left to actually reach equilibrium based off of this K value. So equilibrium concentrations. So this is going to be 1 plus X, and this is going to be 3 minus 2X. Okay, you can leave the 0.0 in if you want. You can drop it if it makes it easier for you to solve the question. Just remember that when you actually do go back and finish answering the question, these had 1 decimal place in them. Okay, so we have that our Kc is equal to the concentration of NO2 squared, and that is divided by the concentration of N2O4. Okay, so even though we're shifting in the opposite direction, we're not going to change these around, right? Sometimes you guys are like, oh, but I need to flip these because I'm shifting this way. We don't want to do that because the Kc number that we have right here is for the forward direction. So if I were to flip these around, I would also have to take the inverse of that Kc. If I'm taking the inverse of both sides, I may as well just leave it the same and not do that additional piece of work, okay? So Kc 0.023, this is going to equal 3 minus 2x squared divided by 1 plus x. Okay, so I would probably suggest graphing this one. It's not a very pretty one to actually go about trying to solve using the quadratic. You definitely can, it's just going to take you much longer. So I'm going to go to the graphing option on my calculator. On y1, I'm going to put 3 minus 2x inside of brackets squared divided by, inside of brackets, 1 plus x. And then on y2, I'm going to put 0.023. I'm going to graph it. Once my calculator decides to graph it, I am going to get it to calculate my intersect. So, get that x equals 1.38. Okay, there is a second positive x value for this one. My calculator's not giving it to me right now, but I want to say it's 1.6. And this is where some of you with Casios tend to have issues with this particular question because your Casio gives you this answer and it refuses to give you this answer. I'm not sure why that is. It seems to be associated with which Casio you have. I know you guys have like a big kind of circle button looking like thing over here. And I know if you hit the arrow tabs, it can swap between the two numbers, but some versions of the Casio seem to not have that feature, and I don't know how to get around that. You definitely practice kind of is usually the best bet. So out of these two answers, right, normally when I do these questions, I only actually get one realistic answer. And the reason I only get one realistic answer is x can't be a negative number. But in this case, I have two positive numbers. So how do I decide which one is right and which one isn't? Well, in this case, if I do 3 minus 2x, if my x was 1.6, I would get a negative number, right? Because 2 times 1.6 is 3.2, which is bigger than this 3. I can't have that, which is why this isn't actually a legit answer for this question. And this is the answer that I need, right? So normally out of the two answers, only one is positive, which is why it's not really an issue. I don't have to decide. But in this case, because both of the answers are positive, the correct answer is going to be the one that when I put it into the subtraction option, actually gives me a positive number for a concentration. Because the smallest concentration you can have is 0. It's not a negative number. You can't get less than 0, okay? So, I'm going back to the question to actually finish solving it. So the concentration of N2O4 is going to be 1 plus x, so 1 plus 1.38. We're allowed one number after the decimal place, so we're going to have 2.4 moles per liter. Okay, then the other one is going to be 3 minus 2 times that 1.38. So again, we're only allowed one number after the decimal, so it is going to be 0.2 moles per liter. Okay, so like I said before, if you mess the question up and you assign this as a negative and this as a positive, all you would find is that both of these answers would be negative and you wouldn't actually have a positive. And you could fix that by just swapping the signs around and then swapping the sign on x. You don't have to erase the entire question. It doesn't, I don't want to say it doesn't change anything, but it just changes the sign. Okay. With that said, though, don't assume that every time you get a negative x that it's okay and you can just flip the sign. This is only valid if you had all initial concentrations. If you have products starting as 0 and you get a negative x, I promise you, you have done something wrong and you need to go back and fix it. Okay, it's not possible to do that. Obviously, if it's just one of the answers that's negative, the other is positive, you're good to go. But if you're not getting a single positive answer for X, something has gone wrong. You need to go back and you need to fix that, okay? So not really very common to see questions like this on a diploma. They require a lot of work. Diplomas on multiple choice and numeric response. You'll sometimes see like the theory-based question of which way would it shift. So it is important to be able to recognize what that numerical value of Kc tells you and how to be able to use that to predict which direction it is going to go. All right, so that basically wraps up the calculation part of the first half of equilibrium.